Dispersion of white light. What happens when a beam of white light strikes a prism? When a narrow beam of ordinary white light is passed through a glass prism, different wavelengths travel through the glass at different frequencies and appear as a continuous broad band of different colors, called the spectrum. This phenomenon, by which a ray of light splits into its constituent colors when it is passed through a transparent medium, is known as dispersion. Find out more facts about the spectrum yourself.
We often face this phenomenon in our lives. However, we hardly ever notice it. But if you pay more attention, you will see that dispersion always accompanies. For example, it manifests itself in a rainbow. I bet you won't find a person who has never admired the rainbow. At first sight, the rainbow may seem very simple for you. However, it includes complex physical processes. Dispersion of light stands for a ratio between the light refraction factor and the light wavelength. Newton's prism experiment, as part of which the light is decomposed into a spectrum using a trihedral prism, experimentally proves the phenomenon of dispersion. Newton proved that if white light passes through a glass prism, it will decompose into 7 rainbow colors, i.e. red, orange, yellow, green, blue, indigo, and violet. This means that white light is not actually white. Vice versa, it includes all the above colors. Dispersion occurs as light rays with different wavelengths propagate in transparent substances, i.e. optical environment, at different speeds. Generally, the smaller wavelength is, the greater the refraction factor and the smaller light speed will be. In incandescent solid and fluid bodies, yield a continuous spectrum, while incandescent gases yield a discrete spectrum typical of such substances only. Then you see light is white, but the world is colorful.
This video is going to go over the basic lab procedure for doing the Snell's Law activity. And I've got a laser level right here. I've got a protractor. You'll be using a pencil, not a pen. I'm using a fat Sharpie marker so you'll be able to see the lines from this distance in the video. And then you have a piece of plate glass, all that on top of a piece of paper. To begin with, I'm going to put the glass on the paper and I'm going to draw an outline of my little piece of glass. So here's an outline going all the way around it. And held it in place. Now I'll slide it. Be careful. Some of these pieces of glass have little chips on them. I don't want you to cut yourself on it. So I'm all set up there. Now I want to draw a normal line. So I'll pick a spot on the glass, on the front surface, make a little mark, slide the protractor over, right there at the hole is where I'll put the mark. Now I'll line it up so it's 0 to 180. Up here at 90 degrees, I'll put another little dot. Connect the two dots, and that's going to give me a line that's going to be normal to that surface. So here we go. Nice long line, both sides of it, so that's normal to the surface. This is going to become the boundary line. So what I'll do is take my laser level. There's a little switch on the back of it. I'll slide it up and it'll turn on. You'll see it glow at the top. Hopefully this all shows up on this low light that I'm using. And I'll put it over here. And that's going to be my incident beam coming right there at that intersection between the normal line and the boundary. And I'll take my piece of glass and I'll put it back into place right here. So I'll line it up even with my outline. Now I've got two light rays. I've got one light ray here. This is going on top of the glass. In fact, I can even block it. So that's just going on top of the glass right there. And then I've got another light ray over here, and that's where the refracted ray is exiting the glass. So it bends in the glass and then it comes out up here. And that's what I'm interested in over there. So I need to be able to draw my incident ray and my refracted ray. I know that's right at the intersection between the normal line and the boundary. I'll put a dot right here. That's going to become my incident ray when I draw it. And I'll put another dot right here. Now this is really faint, might be hard to see on this video, but there's a little red line that appears right over here. I should say, right here's a little red line. That's the one I'm after, not this one, not that long bright one that looks so nice. I'm after this one because that long bright one's on top of the glass. That's the one that's going through the glass. So I've got my lines all set up. I'll move my piece of glass. Again, be careful of chipped edges, if there are any. I'll take my laser level, push it off to the side, and turn it off so it doesn't go in anyone's eyes. Then I'll take the protractor and make my marks. So this is going to be the incident light ray coming in here. So that's the beam that's coming into the glass. And right here, this would be the refracted light ray. So that's where the refracted light ray left the glass. So it goes from this boundary along this line to where it leaves the glass. Right there. This becomes the incident light ray. And over here, this angle is going to become the refracted light ray. This is the glass and air.
There are actually 3 shadows which shouldn't be. And we should make it. Now you see it clearly. you can even see the spirals, right? Come closer if you don't see it. There, now you can see it clearly. But it's not nicely traveling.
It loads very fast.
Yeah, it shouldn't be. Now you can see that. And these waves are actually, in an ideal case, like not when I do it, but when other people show it, then it works better. And these kind of waves are actually opposite rotating